So nonlinear systems. What can we say about these? Um, Not much. So, if you notice, I lowered the bar here. I did not say solve this nonlinear system, right? There's a nonlinear system down here. X times y makes it nonlinear. Y squared makes it nonlinear, right? So I have a system of differential equations still, but it's not of the form constant times x plus constant times y for the formulas for dx dt and dy dt, right? So here we're looking for, we can have a little bit of quantitative analysis of this, but mostly qualitative analysis. Um, so here's the idea is we know how to solve linear systems, right? That's what we really understand. So the goal is to describe, use our knowledge. We want to use systems that look like this: dx dt ax plus by dy dt cx plus dy. We really want to use systems that look like that to understand, because that's those we can actually solve by eigenvalues. Um, right. So these kind of systems, linear system, homogeneous systems, these we can actually solve. So if we can use our knowledge of these to learn something about these nonlinear systems, that's going to be the key, right? So here's how we do that. Notice here, so at the origin, right? Um, a system of this form, this purple system, linear system, you're always going to have a stationary point at the origin, right? What do I mean by stationary point? The system's in equilibrium, right? X is not changing, Y is not changing. The system is just sitting there at the origin. It's still, right? And so that's what we're going to do here is we're going to start by solving in the nonlinear system, right? Let's start by solving for equilibrium points. And then what we'll do is we'll build a linear system at each equilibrium point. So how do I solve for equilibrium points? I'm going to say, okay, dx dt, this is, I want this to be 0, and dy dt, I also want that to be 0, right? I want these two derivatives to simultaneously be 0, right? So here I get what? From the first equation, I get that x is 1, that would give us 0, or y is 0, right? And then in the second equation, what do I get? I get y squared. I get that x equals y squared, right? So then um, combining that with the first two possibilities, right? If I combine these two, I get what? I get the points. So x is 1, but then y could be um, plus or minus 1, right? And if I combine these two, then I just get the origin, right? So there we go. So I have three equilibrium points, right? I have 0, 0, 1, 1, and 1, minus 1. So if I'm thinking about the phase plane for this system, right, I know at those three locations, I have that the system is just sitting there, right? It's just a dot. That would be a constant. So another way to say it is that this would be a constant function that solves the system. So for example, like because remember we're looking for parametric curves that satisfy this system. For example, like this one right here, what does this say? This says that that the parametric curve x of t equals 1, the constant function 1, y of t equals minus 1, the constant function minus 1. This solves the system, right? That parametric curve, that's just a dot. It just stays there. That's actually a solution to the system. And if you look at it, why does that work? Well, on the left-hand side, you just have 0 because you're differentiating constant functions. And on the right-hand side, you have 0 because in the first case, because you have, if you plug in those numbers, right, you get minus 1 plus 1, right? So this is 0 because it's derivative of a constant. On the right-hand side is just minus 1 plus 1, plugging in those numbers. And here is 1 minus minus 1 squared, which is 0. And here it's 0 because it's derivative of a constant, right? So um, that's our little um, what these equilibrium points are, right? They're really parametric curves that solve the system. They're just parametric curves that are just given by constant functions, which is fine. So then what else happens from here? Well, I mean, we could start just like plotting arrows, right? It's still a valid, vector field, right? Sometimes it can be helpful to do that, right? Let's graph a few more that aren't just zero vector for their arrows, right? So let's graph a few more just to see things a little bit. So say I graphed at, say at 0, 1, we have 0, 1, we have, so dx dt would be 0, 1, right? And then dy dt would be 0, 1, right? So that means that I get getting -1, -1. So at 0, 1, here's 0, 1, I'm getting a vector -1. Yeah. Right, that's the vector I'm getting. And usually when you plot the vector field in this context, you kind of shrink the vectors just so they're not all crashing into each other. So there we go. There's an example. And fine. Say we did just for let's say 2, 2, right? So what would 2, 2 be? At 2, 2, we would have dx dt. So 2, 2, we do 4 minus 2 is 2. Right, dy dt is 2 minus 4, -2. So there we go. So from 2, 2, from this point up here, we would go to the right by 2 units and down by 2 units. So it would look like, kind of a large magnitude vector that way. Okay. So you could draw arrows and draw arrows and draw arrows, right? And maybe you get a sense of what it's doing after a while. But here's the nicest thing to do is at each equilibrium point, at each of these three equilibrium points, let's build this. Let's build the best approximating linear system for each of those equilibrium points. That's what we're going to do so that we can really describe the graph at each of those, right? So at each of the three equilibrium points, let's build the best linear system that approximates it. And we'll solve that, and it'll tell us what the phase plane looks like at near each of those equilibrium points. So what do I mean by build the best linear system? Well, if you have this purple system that we were talking about before, right? If you have this, so suppose you call this right-hand side, you call it fxy, and this right-hand side, you call it gxy. So then how would you say A? A would be partial f with respect to x, right? B would be partial f with respect to y. C would be partial g with respect to x, and D would be partial g with respect to y. Right, so those are the four coefficients if you wanted to state them in terms of derivatives, right? Now, when it's a linear system, you don't need to state them in terms of derivative. You just say, hey, there's the constant, right? But if you have something nonlinear, well, this is a way to extract what that coefficient would be. It's by differentiation. So that's what we're going to do, right? So you can still do this even when it's nonlinear. That's the beauty of it, right? These partials, even though it's not in the form ax plus by anymore, right? So that's what we're going to do. And this, in fact, has a name. This is called the Jacobian. So the Jacobian is exactly that. It's the, right, the Jacobian is this matrix, df dx, df dy, dg dx, dg dy. Right, this is the Jacobian. And the Jacobian, it might look very familiar from top three, if you did change of coordinates, right, into 3 dimensions, where you do the determinant of the matrix of partials, right? Also, one thing I should mention, some people say this is the Jacobian, the matrix itself. And then they'll say determinant of the Jacobian when they mean the determinant. Sometimes people just say that the Jacobian is the determinant of that matrix. You'll see it stated both ways. Here I'm using it as the matrix itself and not the determinant of it. But just a heads up, you will see that used. Sometimes when people say Jacobian, they mean determinant of the Jacobian. Here I just mean the matrix, no determinant. Okay. So this is something we can still do for a nonlinear system. So for our example up here, right, let's take our example. So let's find the Jacobian, right? And in general, the Jacobian will depend on x and y, right? Because they could be in those formulas. So let's find the Jacobian for each equilibrium point of this system, right? So what's the Jacobian? Like we said, is, let's see, so it's going to be partial x, partial y. That's going to be partial x, partial y. Right. Right. So there's the Jacobian in general. Now let's do this for each point, equilibrium point that we found. So at 0, 0, what do we have for a Jacobian? Our Jacobian of 0, 0 becomes right when we plug 0, 0 into the Jacobian formula. That's what we get. So what does it mean? It means that near 0, 0, the linear system that best approximates it is this system, dx dt equals negative y, dy dt equals x, right? And then you could solve this using the eigenvalue method, right? If you do this, if you do the eigenvalue method, you'll get imaginary roots there. Partially just because, why do I know that? Well, because you can actually guess, you can do a solution by inspection here, right? At least one solution, right? You can say, okay, if I let if I let x of t equal cosine t, and if I let y of t equal negative sine t, that absolutely works in this system, right? So that's why I know there are imaginary roots, because I'm getting sines and cosines as solutions. So what this tells me is I have some oscillating solutions, right? And I can even do, if you want to make that a little more rigorous, you can say, okay, this is the determinant that we're working on here. Yeah, right. So there's our determinant of a minus lambda. There are those imaginary roots, right? So what do you get for your solutions then, right? The solutions you get e to the I t times the eigenvector. So then, but then this then becomes sine to cosine, right? This is going to become cosine t plus I sine t, right? And you multiply it into v and so on. So what is this going to look like in the phase plane? And of course you could do that, in more detail if you need. Well, in the phase plane, it's going to look like an equilibrium point. And then it's all gonna, if you look up here, you had that point, that vector up above it, right? And that's kind of what's gonna happen here, it's rotating this. There we go. Right, so that's what these parametric curves given by sines and cosines would look like. And how do I know it's rotating counterclockwise instead of clockwise? Well, that's where that graphing that one arrow really helped, right? It shows you the direction. Okay. Then what else happens? What happens at these other two? What happens at 1, 1? So 1, 1, what do we have? I have Jacobian of 1, 1 is 1, 0. There we go. 1, 0, 1 minus 2. Right? So now do the spectrum on this. Right, so determinant A minus lambda 2. There we go. Right, so here, what do we get? The angle zeroes out. Here, I think lambda is 1 or minus 2. So then these are eigenvalues, and each of these will have an eigenvector, right? Some v1, some v2. So that gives us up here at the point 1, 1, right? It gives us something rotating up there, right? Well, rotating at the origin, and then it has to kind of interact with this, right? So minus 2, lambda equals minus 2, that's going to give us a e to the, oh, just happened. God. This is going to give us a, e to the minus 2t. This is going to give us a e to the t, right? Right. So now, yeah, because it's e to the minus 2t, right, whatever happens on the v2 axis is going to shrink towards the that equilibrium point, or something like that, right? As opposed to what happens on the other axis is going to go away from it. And here I'm just kind of lining up the what that looks like against the that rotation, right? Okay. Now we also got to do minus 1, right? So at 1, comma, minus 1, what do we have? 1. So now, okay, now this, the equilibrium point 1 at minus 1. Let's plug that in as well to our Jacobian up here. What do we get? There we go. 1, 0, 1, and 2. So I'm plugging 1, minus 1 in here. Right? 1 and minus 1. Oh, this one up here should be -1. Right, y is -1. There we go. I knew something looked off. So there we go. There's the right thing now. And what is this? If I do this determinant, so determinant a minus lambda I, right? So this gives us what? Lambda minus 1 minus lambda times 2 minus lambda minus 0 equals 0. There we go. So our lambdas here are distinct and real, right? So again, this will correspond to something like this, And this will correspond to something like this. Um, what those V1 and V2 are, we could solve for it, but I mean, they're just approximations anyway, right? So what that's saying is in one direction, the magnitudes are going to get squished into the point. And the other, there we go. Right, so that's kind of the two straight line solutions. Um, then from there, it's kind of just stitching everything together. And like I said, stitching it together qualitatively, right? So there's a right, and these have one of each. There we go. So that's what the phase plane looks like. And what's interesting is you can kind of see what these solutions are doing, even though we haven't solved, right? And it's like out here, it's gonna, at some point it just breaks, never comes back. Here we go. See, those greens are random solution curves that kind of follow the behavior of all three equilibrium points. So that's it's how to predict roughly the solution, the qualitative solution, without doing much math. Right? So solving these are really, really hard. So we typically won't. All right, great. Thank you. So there is Jacobian. Uh, there we go. Jacobian approximation for nonlinears.